Like we've got a pretty good number in. We'll have a few more coming in, but thank you so much to everyone who's joining us today. Welcome to our webinar. This is part of our Young Scholar webinar series on climate change, macroeconomics, and finance that's organized by the E-Axis Forum. Today, we're very happy to have Adam Bauer present his paper, The Timing versus Allocation Trade-off in Politically Constrained Climate Policies. This is co-authored work with Stefan Holligate and Florent McIsaac. Just to give some introduction about Adam and his background, he's an NSF graduate fellow at the University of Illinois, Urbana-Champaign, and a consultant for the World Bank Climate Change Division. He's an interdisciplinary scientist working both the physics and climate risk and how climate risk impacts the economy. He has also worked on decarbonization, investment strategies, and the political economy of climate change. He holds a PhD in physics from the University of Illinois, which he just recently received. So that's a big congrats to him. I'm sure he's very happy about that. And we're very excited to have him present, particularly as someone with expertise with a physics background and also some very interesting work in economics. So uh, I think that's all I have. Adam, I will turn the time over to you. We'll go for about 50 minutes or so, and we'll do Q&A at the end. So anyone who has questions, feel free to put them in the Q&A or chat. We'll try and do some clarifying questions as needed during the seminar. Otherwise, we will do a lot of Q&A at the end and be happy to hear your questions. So Adam, it's all to you.
Cool. Thank you so much, Michael. And thanks for everyone for coming. I'm really excited to talk about my work today on the timing versus allocation trade-off in politically constrained climate policies. Again, this work was done in collaboration with Stefan Hollingate and Florent McIsaac, both of the World Bank. So why don't we jump right in with the motivation for this paper. So it comes as no surprise to know that policymakers are facing plenty of political economic constraints in implementing their various climate policies. Current evidence would suggest that while many countries have politically or climate-focused climate policies, they're often sectoral in focus because of political economy constraints. And these can come as various mixes between sectoral policies in carbon taxes, ETS is only coming part of the system, and so on and so forth, because some sectors of the economy are just politically out of bounds and untouchable for climate policies at this time. And even when you have a sectoral policy, they can often have a number of different exceptions. They may only cover a share of the total emissions, as I mentioned. As you think about this, like the EU, European, or the emissions trading system in the EU. They could have exemptions on different fuel sources, like air transport fuels, or have different prices, even if there's a carbon price in place. There might be a higher tax on liquid fuels than coal, depending on how the various kind of political power of different power sector actors are kind of distributed within that country. And so the kind of goal of this paper, getting right to our kind of main goal, is trying to generalize the different approaches that these policymakers can take when navigating the political constraints that they face. One opportunity, or one way that they can navigate these constraints, is to implement some suboptimal heterogeneous policies in the near term. And when I say heterogeneous, and throughout this talk, what I mean is heterogeneous in the sectors that they cover, just covering the power sector, just covering the industrial sector, just covering transport, and so on and so forth. And these policies, again, can come in a lot of different forms, but speaking generally, they can be sectoral carbon prices or industrial policies or command and control regulations that just hit specific technologies or specific sectors at a given time that the government would view as being kind of politically expedient enough where they can pass a climate policy in that sector without causing too much of an uproar. And this strategy, coming along the lines of implementing some suboptimal policies in the near term, what we're going to argue is that these policies are sacrificing their sectoral coordination in favor of near-term investments in abating CO2 emissions. So the way to kind of think about it is that they're preferring the timing of their policies to the near-term implementation of a policy over having the perfect sectoral coordination. As we all know, when you implement the kind of first best carbon tax, right, it's somewhat uniform across all the sectors and so on, and then the sectors, depending on their costs, will abate accordingly. But in this case, you're kind of getting rid of that coordination part in favor of implementing something in the near term. We can compare this kind of suboptimal heterogeneous approach with a second approach, which is that you delay implementing your policies for some amount of time, after which you might implement a much better policy in the future. And so instead of thinking about what kind of policy instrument you're using, whether it be carbon prices or industrial policies in the second choice or the second avenue, you can think about the delaying of your climate policies as a policy instrument in and of itself. And there might be a couple of reasons that you would do this. You might think that some number of years from now, things would be cheaper, and so it would be easier to implement. You might have more faith in your political coalitions down the line or something like that, that you'd be able to implement a policy later rather than sooner. You kind of think about the policy of delay in and of itself as a choice, and it's something that we need to kind of understand how that impacts climate policies and the green transition. And the policies in which that you're delaying these policies and after some amount of time you'll implement, the carbon price that covers the whole economy or something like that. These policies are foregoing this kind of optimal timing of the investment, or they're foregoing near-term gains in abatement in favor of this allocation of effort across sectors, right? They're going to put a uniform carbon tax in place and just say, okay, we're gonna allocate the effort efficiently across all the sectors. And so, I'm kind of teeing this up. This is the kind of tension that we're really focused on throughout this paper, which is the tension between how you time your climate policies and how you allocate your effort across different sectors. And we coined this tension as the timing versus allocation trade-off when you're implementing these politically constrained climate policies. That's going to be the central focus of the talk for today. And so our approach is really to probe the cost implications of the timing versus allocation trade-off. And to do so, we're going to develop a multi-sector abatement investment modeling framework, wherein the policymaker can wield two policy instruments. The first is a carbon tax or an ETS. This can either be homogeneous in the sense that it covers all the sectors equally, there's one carbon tax for every sector, or it can be heterogeneous in the sense that there's one tax for these sectors and one tax for these for a different set of sectors. And the second approach is, again, to kind of in a targeted way, delay climate policies either in a set of sectors or across the entire economy. And we'll get a little more precise on what we mean by the targeted delay of climate policies in a minute. So the contributions for this talk and kind of where we're going to go from here, we're going to make three theoretical contributions throughout. The first is we're going to present this multi-sector model of abatement investment that incorporates political economy constraints, PECs, into a subset of economic sectors' decarbonization schedules. So we're going to kind of theoretically formulate the type of model we're going to be using. The second thing is we're going to formalize a set of policy approaches to delaying decarbonization in your politically challenged sectors. So we're going to kind of walk systematically through what does it really mean to delay the decarbonization of a sector? Does it mean to not do anything in that sector? Does it mean to relax stuff in that sector, investments in those sectors? We're going to really try and formalize what we mean by delay. And the last thing from the theoretical perspective is we're going to try and establish a hierarchy of the different costliness of different policy approaches. So different versions of delay will have different costliness, and I'll present a kind of theorem for how to rank these different policy approaches. Secondly, we're going to do some numerical experiments at the end to make two additional points. One is that the economic cost of these different policies increases nonlinearly as decarbonization within a challenged sector is delayed. So the longer you delay, a kind of nonlinear increase in the amount of cost is what we would observe from the numerics. And then secondly, the costliness of delaying a sector's decarbonization is, in our case, controlled by its annual emissions rate, not its marginal investment cost. So trying to really hone in on what's the characteristic of a sector that makes it expensive to delay. And in this case, we're going to find it's the annual emissions rate that really does it in our case. So I'll flash just a quick literature slide just in case anyone wants to take a screenshot and do a dig of their own. Our paper is really nestled within four types of literatures. Obviously, optimal climate policies, second best climate policies, and the political economy are kind of a given, given what I've discussed so far. But there's also this other literature on kind of adjustment costs and socioeconomic inertia that our model kind of includes and is definitely an additional component of this work. So let's talk a little bit about the theoretical framework and the different policy suites that we're going to consider in this discussion. So to give some quick forerunners on the kind of relevant mechanisms in our model, we're considering a centralized planner that decarbonizes the economy such that some emissions budget is not exceeded. And throughout our emissions budget, we're going to define as the global remaining carbon budget B. So for those who aren't familiar, the remaining carbon budget is essentially how much more carbon can you emit before a certain long run temperature target is sure to be exceeded. And that's kind of going to be our framing, but you can generalize the carbon budget here to be any country's emissions budget or its NDC. The same type of framework could be adapted to any one of those policy settings. The economy that we consider has a cumulative emissions level, which will be given by psi, and a set of economic sectors given by I. Now, for every single sector, these are the kind of characteristics that it has. I'm going to quickly run through them just so folks have some context for what we're thinking about here. It has an investment level, X of I, which the social planner can control. So you're choosing an investment level. You have an abatement level in every single sector, a convex cost of investment in abatement technologies. The convexity of this function is what gives our model a representation of adjustment costs. The capital depreciation rate given by delta, an annual emissions rate given by a bar, and a start time, T naught I, before which no investment occurs. So that's kind of a point at which you start the stopwatch and you start the policy in that sector, and we're going to be able to vary that in our framework, kind of apropos of us talking about delay. That'll be one of the parameters we vary. So quickly looking at the optimal policy in the least cost sense, in our framework is if you start an investment immediately, so that T naught I is 0 for every sector, we're going to minimize your discounted costs over an infinite horizon for every sector, discounted at a rate R, subject to a couple of constraints. One is a capital accumulation equation that will translate investment into abatement capital that will obviously decrease your emissions. There's a constraint on the amount of abatement you can do in every sector, given that abatement can never exceed your emissions rate. Psi dot, or that's the rate at which you accumulate emissions in the atmosphere, is given by the difference between the exogenous emissions rate A bar and your abatement rate or your abatement level given by AI. And then finally, your cumulative emissions are always capped at your carbon budget. So psi never is going to exceed B. And that puts kind of a scarcity or makes the carbon emissions in the economy rivalrous between different sectors. And will limit its use, obviously, in the economy-wide. So I could show, the reason I show these sets of equations is to kind of give some motivation for the type of modeling we're considering. I'm not going to show all of the suboptimal policy suites that I'll talk about now. Some of the best advice I ever got about showing math in a talk is to not show math in talks. So I won't give like every single optimization, and I'm happy to dig into those details if anyone's interested in the Q&A. But for the next couple slides, what I'm going to do is I'm going to show the different policy suites as kind of schematics. Before I do that, excuse me, I'm going to give a quick set of precursors for what the characteristics of the optimal policies can be important for when we think about the suboptimal ones. So the model we just wrote down, the optimal policy case, was extensively studied in Voigtlib et al. And Jeam in 2018. We're going to build on that framework by incorporating the suboptimal policies. There's two characteristics of the optimal solution that we need to be aware of when we think about those suboptimal policies in a couple of slides. The first is that after you optimize this problem, you can compute using the optimal path of abatement, the ex post allocation of emissions across sectors. So that's going to be B star throughout our entire discussion. And that's given by integrating the abatement difference between your emissions and your abatement capital stock in the optimal case. And secondly, every sector also has a decarbonization date T star. And T star is essentially when that constraint in the emissions rate and the abatement capital binds when they're equal. And that timing is going to be important for, again, when we think about what it means to delay climate policies. So now we can move into the policy suite. Excuse me, I forgot I have one extra slide. So the first is obviously the optimal policy. And when you implement the optimal policy, you incorporate your optimal carbon tax given by mu star. The effect that has across your set of sectors I in your economy is that for every sector, you'll get some path of investment that looks something like this, where the gray line throughout the next couple slides is going to be the representation of our optimal case. You can look at this investment pathway and find right where that decarbonization time T star is. That's the transition between that kind of declining path and the steady state. And after you find that T star, you can compute the optimal allocation of emissions across every sector of the economy within your first optimal policy, within policy suite 1, as we'll talk about, as we'll refer to it throughout the talk. The next policy suite we'll consider is we're going to take these two sectors and we're going to bifurcate them into two groups. So there's going to be a set of heterogeneous policies that we'll discuss. The set N is going to be our politically non-challenged sectors, and of course, this is all comparative. There are, some sectors are, every sector has, some amount of constraints that you have to navigate, but at least for the sectors N, they're not challenged relative to set C, which is going to be our politically challenged sectors. Those are the ones that are having these political economy constraints that are blockading climate policies, and the ones we're going to have to navigate those constraints in order to implement something. And so the first policy suite, which we'll refer to as policy suite 2, is a relaxation of effort policy. And what we mean by this is we're going to change the allocation of efforts across the economy in terms of the emissions. So we'll take away some amount of emissions from our non-challenge sectors, in this case, the factory there, and we'll give it to the challenge sector C, and that will increase its emissions allocation. So again, this is just changing the amount of emissions that every sector gets when you implement the policy. What happens is the challenge sectors C get a carbon price as a result that is less than the optimum, which obviously has an impact on its investment pathway. There's lower investment in the near term, and the investment gets spread out over the course of the policy period. And when we look at this schematic, it becomes very clear what we mean by delay in policy suite 2 within the relaxation of effort policy suite. What we mean is that we're taking this T star, this decarbonization date, and we're pushing it into the future by delta T. And we're doing so by increasing the amount of emissions that it has allocated to it in its ETS or in its carbon price. So this is what we mean by delay in this case, is that delta capital T comes about by lowering the carbon price and spreading out investment over time. So that's the first one. The second one, we're going to keep our heterogeneous picture, and now we're going to change both the allocation of effort and the timing of investment simultaneously. So how we're going to do that is we're going to lower again the amount of emissions allocated to the non-challenge sectors N. We're going to give them over to the challenge sector C. But the difference now is in policy suite 2, the one I just talked about, there was some policy implemented immediately in both sectors. In this case, there's going to be a policy implemented immediately in the non-challenge sectors, naturally. So its T naught factory is 0. So there's some amount of effort happening immediately in those sectors. However, for the challenge sector, what's going to happen is we're going to essentially use up all of the premium immediately and just delay the implementation of the policy by delta T. So the same amount of allocation is given to that sector, but the policy within the challenge sector is going to be delayed by some number of years. And so what happens is you implement that policy, and there's no investment in the first delta T periods, and then actually the same exact investment pathway happens afterwards. And again, you're delaying the decarbonization again by delta T. So it's important in this case, the same exact carbon price is going to be implemented. It's just going to be delayed implementation by some number of years in this case. And that brings us to the final policy suite that we'll consider during the talk today, which is an economy-wide delay. So we're going to take our heterogeneous picture that we just took and merge all the sectors back into the same group given by I, and we're going to change the timing of effort in this policy suite. So we're going to forget about the previous optimal allocation of effort, and instead we're going to say the entire economy is going to delay their climate policies by delta T. And then the emissions budget for the entire economy is given by B minus the economy-wide emissions rate multiplied by the delay time. Okay. So when you do this, after some amount of time, because when you implement the policy, there's less emissions relative to the previous case, the carbon price is going to be greater than the previous optimum. What that means within a given sector is there's still going to be no investment early on, some delta T. There's going to be no investment, but afterwards there's going to be an enhanced rate of investment because, again, remember, we are considering a situation where the climate goal is always reached, right? Carbon budget, no matter what, is still never breached. Obviously, in a case where there's, delaying carbon policies and all this kind of stuff, it's not beyond the pale to think that the government may relax its climate policy goals altogether, right? But we're kind of not dealing with those details here and thinking just about, okay, if we're going to change the allocation or change the timing, how do you navigate, navigate that within the constraint of we're always going to reach this goal, right? Okay, so with those insights in mind, in terms of that kind of schematic in mind of the different policy suites we're considering 1 through 4, we'll just flash the main theorem of the paper. And again, I won't go through the whole proof, but obviously folks can ask about it if they're interested. And the main point is that if you fix that delta T between all of the different policies, what you find is that policy suite 4 is the most expensive of the responses to the political economy constraints, followed by policy suite 3, and then 2 being the least expensive. So plain English is that the cost of policy 4 is bigger than 3, is bigger than 2, is bigger than the optimum for a fixed amount of delay. If you fix that delta T between all the different policies. And so we can already kind of formalize this as a take-home point, which is the distortion of optimal timing of your investment is in general more costly than distorting the allocation of effort across sectors, right? Basically, there's another way of saying that policy suite 4, where we only tweak the optimal timing, is more expensive than policy suite 2, where we only tweak the allocation of efforts across sectors. And so as a kind of corollary to that, what we can say is that doing something in the near term, even if the policy is suboptimal, is cheaper than doing nothing and implementing the optimal policy later, again, all else being equal. So with this kind of theoretical framing in mind, we're going to move to the numerical experiments of our section of the talk. And the reason for that is the theoretical arguments that we just made or the theoretical results that we find in the paper give us a general hierarchy for the different policy approaches that we consider, but in general, it does not inform us on how large that gulf is. You could obviously imagine if policy suite 4 is bigger than policy suite 2 by fractions of a percent, that's going to be much different than if it's bigger. Policy suite 4 is more expensive by 10% or 20%, obviously. It's going to be important information for us to convey. And so we designed a set of numerical experiments to probe the difference in costliness for the different policy suites. So we take some data from the IPCC, their working group 3, to calibrate these numerics in terms of the different sectors we consider. We're considering 7 here, their emissions rates, their capital depreciation rates, and their investment cost levels. And so we're going to consider throughout 2 exemplary politically challenged sectors in our experiments. The first is we're going to think about energy. And there's 2 reasons for each of these sectors I'll talk about for why we're interested. The first is from kind of a parametric perspective. Energy has a really high abatement potential and a low marginal abatement cost. So kind of can make us understand, okay, how does it, how costly is it to delay a sector that's emitting a lot, but actually doesn't cost that much to abate in? But also from a kind of narrative perspective or from a political perspective, there's plenty of situations where the fossil fuel lobby is really strong and delay climate action within the energy sector. There's plenty of examples of that going around. So we'll think about this as in our first case. And then secondly, we'll think about heavy industry. In industry, from a parametric perspective, it's moderate abatement potential, about half of that of energy, but it still has very high investment costs. So a very expensive sector to delay. And of course, there are plenty of political reasons where someone might be okay with delaying the decarbonization of their industrial sector. It could represent a situation of a nation concerned with competitiveness of their domestic industries. And so they're going to kind of favor those industries by not decarbonizing them as quickly as might be optimal. And so we're going to start this discussion by looking at the streams of investment effort for every sector. So this is your investment effort in billions of dollars a year for every sector that I just listed. And to go through what the different lines are in each one of these panels, the gray line, solid line, is the first best policy. So that's your optimal case. That's how each of these sectors in the perfect scenario would be allocated effort. The blue dashed dot line is the policy suite 2. Again, that's the relaxation of effort policy case where we only change the allocation of effort. Energy is decarbonized. The decarbonization of the energy sector in the dashed dot blue line is delayed by 10 years. So we're fixing the delta T at 10. You can kind of see this. I hope people can see my cursor in the panel F, where the steady state is reached later than the gray line. Policy suite 3 is the solid blue line, again, where energy is delayed by 10 years, but now it's in that kind of shifting the policy and energy by 10 years and not implementing anything in the near term. And then finally, policy suite 4 is when we have the economy-wide delay. That's the pink dotted line. And in that case, we're delaying economy-wide investments by 10 years and then implementing the first best carbon price, given the constraints of having done nothing for the first 10 years of the policy. And so what are the take-home points from this figure? The first is that we can kind of already see that policy suite 4 is causing the biggest changes in the investment paths. If you look at any of the sectors, I think particularly, looking at industry in panel B or agriculture in panel D, you can see how, the blue lines are different than the gray line, but it's not so different. Whereas the pink line, you have this kind of huge deviation in the investment pathways in those sectors in particular. And to that point, focusing on transport industry and agriculture, we can see that these sectors are the hard to abate sectors in this case, experience the biggest changes in their investment schedules. What we mean by hard to abate here is just that the marginal investment cost is high, and the abatement potential, that being the emissions rate, is non-trivial in those sectors. So you have a lot of work to do in those sectors, and they're of high cost. And finally, this kind of change in their investment pathway is consistent with these hard to abate sectors having their decarbonization dates change the most. So you can look at the optimal path and how much sooner you have to decarbonize those sectors relative to the optimal in the case where there are political constraints. And now, again, we can look at, instead of looking at the other sectors that are politically challenged, we can zoom in on the energy sector, which is, again, the policy or the sector that was politically challenged in these experiments. For the politically challenged sector, policy suite 2, what we can see is that this blue dashed dot line allows the investment to be smoothed over the course of many years, which allows some of the costliness to be spread out over time, which limits the cost increases, relative to policy suite 3 and 4, which again, 3 is just with it being shifted, and then policy suite 4, of course, you have this really large increase in investment early on, which is made more expensive by the presence of adjustment costs, again, within our framework. So that's kind of one of the main keys of this, is that when you have these large deviations in the necessary amounts of investment, adjustment costs make that even more expensive, which really drives up the cost of these suboptimal policies. So what's causing these big changes in the investment pathways? We can look at the carbon prices that are implemented in every single one, in every policy we're considering. So panel A, the leftmost panel, is the carbon prices for policy suite 2. Panel B is policy suite 3, and panel C is policy suite 4. Now, these are plotted as an index where 1 is the first best policy's carbon price, and then every change after that is all relative. The orange lines in panels A and B are when industry is the challenge sector. And the dashed lines are the carbon prices for the non-challenge sectors. Okay, so that's why they're greater than 1. Those are the sectors that are getting some amount of emissions taken away from them, tightening their budgets, and increasing their carbon prices. The solid lines are the carbon prices for the challenge sectors. So the orange solid line here is the carbon price for industry, and blue, again, is for energy. And then pink, again, is every sector's carbon price, because in policy suite 4, they're all kind of grouped once again. So what are the takeaway points from this? In panels A and B, what we find is that the changes in the carbon price for policy suite 2 and 3 are roughly linear in the delay amount. So you delay by 1 extra year and you're getting kind of a unit change in your carbon price. There's not any real non-linearities that we notice in those first 2 panels. And that is in strong opposition to what we find in panel C, where the carbon price is strongly nonlinear in the delay um, for policy suite 4 with the economy-wide delay. And one more thing to notice is that the carbon price increases or decreases in panels A and B are driven by the emissions intensities of the sector. So again, recall that I mentioned that industry is about half of the emissions rate that energy does within our calibration. What you find is that if you squint, it looks like about double compared to the one line. It looks to about double of a decrease and about double of an increase here for industry for energy relative to industry. And so to kind of hammer on that point for a moment, what one can compute is the emissions premiums needed to accommodate the political constraints in every policy suite, considering the two different sectors that we have. So focusing on policy suite 2, again, the relaxation of effort case, we notice that the sectoral emissions intensities for energy is bigger than industry. And then when you break it down by how many years of delay you have, for 5 years of delay, the premium you have to allocate for energy is bigger than industry by about 1%. And then for 10 years of delay, it's about 2% difference between the premium you need to allocate for energy relative to industry. And again, if you go right down the table, you'll notice the same exact thing where in policy suite 3, the emissions intensity is bigger for energy than it is industry. And this time it leads to about a double change in the premium for energy compared to industry. And again, same deal for 10 years of delay. And then finally, when you delay the entire economy, you have an effective emissions intensity for the entire economy as being about 38 gigatons a year. And that, of course, leads to super large premiums in terms of emissions being reallocated, far more than any one sector, obviously, than we consider, and leading to very strong differences in the carbon price. So what we have here is the carbon price changes are being driven by the emissions intensities because the emission intensity controls the amount of emissions required to enact your second best policy. It controls the premium of emissions you need to reallocate within your economy in order to accommodate those political constraints that we impose. Okay, so the last thing I'll show from the numerical experiments before I close with the discussion is the aggregate cost implications of each policy suite. So the left-hand policy is showing just monetary costs. Panel B is the index relative to the first best policy is equal to 1. And the final is your marginal cost of delay. So that's the change in the policy cost per unit delay in decarbonization. And again, same line styles as we had before, where the dash dot lines are policy suite 2. The orange is where industry is decarbonized, or industry's decarbonization effort is relaxed. Blue is for energy. Solid lines are policy suite 3, and the pink line is policy suite 4. Take-home points here being that the increase in total policy cost is nonlinear in delay for all policy suites. Although for policy suite 4, it's very strongly nonlinear, and you can see that by looking at any of the panels, but especially panel C, you can see the marginal cost is certainly nonlinear there. Whereas for policy suites 2 and 3, it's actually very weakly nonlinear, which is not really what we expected, but you see that there's not a huge nonlinearity there. The marginal cost is slightly linear, but again, it's very weak, especially relative to policy suite 4. So despite these different qualitative similarities between the nonlinearity, the changes in the investment pathway, the changes in carbon price, the overall quantitative differences are significant. Obviously, if you delay one sector, if you delay energy by 10 years under the policy suite 2 prescription, you're increasing your costs by about 2%. But if you delay all the climate policies in your economy by 10 years, okay, you're looking at like a 50% increase. So huge differences. And even between policy suite 2 and 3, just for the energy sector, you're looking at a difference of 2% versus 12% for a delay of 10 years. So still, even within a given sector, you can have these large differences depending on the particulars of the policy that you implement to accommodate your political constraints. And so the second take-home point here is that for our numerical experiments, the cost disparity between these different policy suites is substantive, meaning that the way you navigate these political constraints does indeed have large, potentially large implications for the costiness of your policy, which is shown by our numerics. Okay, so I'll close with some discussion of some different points or some policy relevant points in our work um, before we kind of open it up to questions. One is, again, I want to just focus again on policy suite 4. It's it's easy to believe that while this is kind of this is the kind of brute force application of delay, where you're just delaying all of your climate policies. In the near term, obviously, this seems the most politically expedient because you're just not doing anything um, in any sector. But it's kind of important to remember that it's unclear if this is politically expedient over a longer time horizon. Because obviously the required carbon price that you need to implement some years from now non-linearly increases in the delay amount. So if you wait 5 years, you have to implement a 50% bigger carbon price, or 10 years, you have to implement a 3.5x for your carbon price. And so here it's really important to kind of remember that if one hopes to delay your economy-wide decarbonization within the type of framework that we've discussed here, then one is also betting on an exceedingly favorable political environment in the future. So you're betting that not that you can implement the 2020 or 2025 carbon price 5 years from now, but really you have to think about it like you have to implement, 1.5 2025, in 2030 or whatever the case might be. The second implication that I want to talk about is, bringing back this point about what drives these different sectors' costs of their delay. So what we did is you can plot the change in policy, so the relative policy cost on the y-axis in every case. On the x-axis is the sectoral characteristics, the capital depreciation rate, the abatement potential, and the log of the marginal investment cost given on each x-axis there. And the top 3 rows, A, B, and C, are for policy suite 2, where the effort is being relaxed, and then policy suite 3 is in the bottom where you have the policy in the challenge sector being delayed. So every color of the dots is a different sector that's being treated as politically challenged. And the pluses are the 5-year delay, and the circles are for 10 years of delay. So there's different amounts of delay here. And what you can do is do a super simple regression of the sectoral characteristics against the relative policy cost increases for every sectoral characteristic and each of the delay amounts to be considered. And obviously, if you look at this table, it's very clear that the emissions rate is the dominant factor. In policy suite 2, it's almost exclusively the leading cause. In policy suite 3, it's a little less so, but still it's much more important. It still outranks the other sectoral characteristics in importance in policy suite 3. And so that's kind of our final take-home point, is that sectors with high emissions intensities, not necessarily those with high marginal investment costs, are the most expensive sectors to delay. And again, this comes back to our point about when you delay policies in a given sector, you have to think about how much of the budget are you using, or how much of the emissions budget are you using to delay that sector, right? And so for sectors with high emissions intensities, those are the ones that are going to eat up more of your budget, and therefore are the ones that are the most expensive to delay. So a couple more things. One is we consider throughout a least cost approach. So we're just minimizing costs, but of course that doesn't place value on avoiding climate damages sooner or later. So the one thing we did was compute the ex post optimal temperature pathway for each policy suite using the transient climate response to emissions. For those who aren't familiar, the TCRE, or the transient climate response to emissions, is a kind of linear scale factor between the cumulative emissions in carbon or in carbon dioxide and the average global temperature rise over some time horizon. And so again, same line styles as before, where the gray down there is the first best policy emissions path on the left and the temperature on the right. And then the dashed out line is policy suite 2, solid colored is policy suite 3, and then policy suite 4 is the pink dots. And what we find is when you zoom in on the temperature pathway, there is some fairly important heterogeneity in terms of when the different temperature thresholds are reached. So in our case, we considered throughout a temperature target of 1.7 degrees. And what we find is that when you zoom in on policy suite 4, the year that these different temperature thresholds are reached can vary a good amount relative to the optimum. So in the optimal case, you have 2040 is about when 1.6 degrees is reached, and get about 2036 for policy suite 4, and less so for the other policy suites. So It's not so important for 1.6, but for 1.7, it's much different. So probably for the optimal case, you're reaching 1.7 by about 2100. So you're kind of, by the end of the century, you're reaching full decarbonization there. But in Policy Suite 4, you're decarbonizing before 2060 because you reach your temperature target, meaning that there's no more emissions left in your budget. So not only does that mean that you have to achieve decarbonization faster, but you're also living in a 1.7 degree world for 40 additional years following the Policy Suite 4 and even Policy Suite 3 or something like that, which is again not so different than Policy Suite 1 in terms of when you reach it, when you reach the temperature target. It's still 20 years of living in a 1.7 degree world. So it's still some differences there in terms of the climate damages that would be implied. Finally, just some limitations and possible directions for discussion. We neglect a number of risks in the climate econ system, which would likely increase the cost of delaying policies. You can think about climate risk, both from an aleatoric perspective or an epistemic perspective. You don't know exactly the carbon budget, but there's also climate shocks that would be transient, but also impact potentially your policy that we could have considered. You also could have considered things like uncertainty in investment costs as another potential. We only use one carbon price as our policy instrument. In the future, we could think about, also thinking about subsidies or command and control regulations, etc. For the purposes of this talk, we really wanted to focus, again, just explicitly on this delay versus tax or delay versus policy kind of trade-off. But obviously, in the future, we could enrich that kind of policy angle of the discussion. We neglected here the impacts of learning and technology change, which would likely alter our quantitative results. Obviously, anytime you delay these climate policies, you're missing out on some endogenous learning gains that would likely increase the cost of the policy. And finally, we consider kind of a global case, but if you adapted this to any one country that's within a broader international community and trying to do the same type of optimization, the free rider issues, as they so often do in climate policies, could rear their head. One is, there could be substantial global knowledge spillovers, again, going back to the learning point. But there also could be a case where some country or a set of countries implement some grand scheme of carbon removal, which would effectively may change your carbon budget that you face as a nation over time, right? So the rate at which you use up your budget as a function of delay might be dependent on the removal strategies of other nations. So something to keep in mind. Obviously, I think it was a little bit beyond the scope of this paper in particular, but definitely something that we're mindful of and could be a direction to improve the paper in the future. So yeah, with that, that's all I have for today. If anyone has any questions, obviously feel free to ask or shoot me an email. My email's there if you wanna chat, or if you wanna talk about the working paper, need a copy of the working paper, anything like that. Just let me know. You can email me or find me on my website, and I'll be more than happy to chat. So looking forward to people's questions, and thank you so much for listening. Appreciate it.
Perfect. Thanks, Adam. Really enjoyed the presentation. So we've got a perfect amount of time now for some Q&A, some comments and discussion.
Sure.
So if anyone, if you would like me to read the question, feel free to post these in the Q&A or in the chat, and I'll go ahead and read them and let Adam answer them. Otherwise, if you'd like to ask the question yourself, you can still post it in the Q&A, but raise your hand using the sort of raised hand function. Both the Q&A and the raised hand function are at the bottom of the Zoom screen in those options. So go ahead with either one of those, and we can have some discussion and questions right now. While we were doing that, one of our PhD committee members had a question that I think would be a great one to start off with.
Sure.
So Olympia, if I'm gonna unmute you, and if you want to turn your camera on, okay, perfect, you're there. Do you want to go ahead and ask your question to start us off?
Hi, thanks a lot. Sure. Can you hear me?
Yes.
Yep.
Okay,
All
that's
good.
good. Thank you so much. Very, very cool paper. I mean, I guess you referred to this at the very end now during the discussion. What I was
Mhm.
wondering while reading the paper is related to the geographical heterogeneity of carbon
Mhm.
policies or environmental policies in general. And apart from this technological spillover you mentioned or carbon captures, I'm thinking of carbon leakage in general. So one country introducing a policy, production networks overarching several countries, and then economic
Mhm.
activity and emissions shifting away from the country with relatively higher carbon prices. And was wondering what you think about this, whether the model allows for this.
Mhm.
Yeah, even considering the optimal case of like homogeneity in sectors in terms of
Right, right,
policies.
right. Yeah, yeah, for sure. It's a great question. Yeah, in terms of the model as it is right now, I think the multi-country case or something like that could be a really good direction to go in. I think right now it wouldn't be able to say anything presently, but in terms of the carbon leakage or something like that, I'm not sure how that would impact what we're thinking about. I mean, the key bit of the model, I think how it would impact it is if you'd have to find a way to incorporate it into the emissions budget of the country or something like that, or maybe it would impact the costliness. I'm not sure. Maybe it depends on how you formulate it. But yeah, I'm not sure. I guess is the direct answer. But it's a good question. Something we should definitely think about a bit more.
Thank you.
Mhm.
Great. Thanks, Olympia. I have a couple of questions, so maybe I'll ask some while we're waiting here.
Mhm.
Um, so first off, I think a really interesting topic. I think it's pretty clear that thinking about these sort of suboptimal policies is what we need to be considering. And, I think there's a lot of
Mhm.
theoretical work that suggests that we know what the optimal policy would likely be in different scenarios, and yet it's not being implemented. So we should think beyond that. So I think that's
Right,
very
right.
nice. I think the question maybe I'll ask, there's a couple of things, so I'll try and start bite by bite here. The
Hmm.
question I'm interested in is, have you guys explored the implications of looking at different carbon budgets? Right? We sort of know that there's this range of potential TCRE values that you could use based on the sort of underlying sort of large scale GCMs.
Right, right.
And there's all sorts of dynamics to think about there. So I'm wondering, one, have you thought about or looked at sort of in your numerical experiments how changing that budget would impact these results and how much that
Mhm.
might matter?
Yeah, for sure. Yeah. So 2 points on that. One is, yeah, in general, the wedge between 1, 2, 3, 4, the wedge between these different suites, um, increases with your ambition, right? So if TCRE ends up being higher than what we consider it right now, right? Which I think right now it's like, well, like 0.4 centigrade per 1,000 tons or something. Um, if you're more ambitious or you have less of a budget, then the wedge between all of these policies grows and grows and grows, right? Same deal if it's lower, or equivalently, if you think about like a more lenient policy goal, like a 2-degree goal or something like that, then the wedge is gonna shrink relative to what we considered here. The second point is we have another paper actually using a very similar model, but incorporating uncertainty in the carbon budget into that analysis. What you find is that if you have an optimal policy under uncertainty in the carbon budget, which is essentially uncertainty in the TCRE, then a lot more of your investment becomes front loaded as a hedge against like some negative outcomes. And so if you kind of miss the boat on that upfront part, because you're delaying your climate policy, then you're going to have an even worse scenario in terms of the differences between those different approaches. So yes, we haven't incorporated the uncertainty model into this one just yet, but we have thought about both of those cases for sure.
Great. Yeah, that was sort of my follow-up question is, have you thought about the implications of what that uncertainty might be? But it
Yeah,
sounds
yeah,
like you
yeah.
have some nice results from that.
Hmm.
Um, so let me maybe ask a second question here. You sort of mentioned this in the concluding discussion, as you were talking about this, sort of immediately my mind turns to sort of the technological investment and these
Hmm.
sort of technological innovations, which you've sort of mentioned there. I mean, you could sort of think about the abatement investment as one form of sort of technological change investment. You're trying to build up a capital stock that allows you to address it. But have you guys had a chance to sort of think about or explore alternative sort of R&D investment type specifications and uh, what that means in your setting?
Yeah. Actually, it's kind of a funny story. Like, I think at some point I was playing around with some version of having technology change in this model, and the short version is we have like another paper. It's like a whole nother exercise trying to incorporate it. So I wrote it down. I like threw it as like a extra slide in one of our meetings, and they're like, "Oh, we should like." I think it's a different paper, or something like that, right? So yes, right. We have thought about it. Something we'll work on in the future for sure. Yeah, I think that goes to the point of like, I think one question that's very interesting if you're going to think about suboptimal policies, right? Is like the kind of path dependence in terms of the policy sequencing that you think about, right? Which is to your R&D point, right? If all you can do, like the US, is like have a subsidy policy or something like that, and that's your near-term investment that we consider, right? You could easily imagine that like even if you don't get the abatement that you would want out of your policy, that R&D could still be justified on learning grounds, right? I think there's a paper by Connor Walsh and Erko Lakis, I think out of Columbia Business School, that talk about the global knowledge spillovers of the IRA and the welfare implications of that. I think it's called Clean Growth, but I don't think it's out yet. I think it's an MBR paper. So yeah, I think that's definitely something we've thought about. And we'll have more to say on that soon. But definitely something I think is super important for this type of analysis, and especially if you're thinking about the suboptimal cases, because that sequencing of policies are going to be so important if you're not just implementing the carbon price immediately and just letting it run for T up until T equals infinity.
Yeah, absolutely. Okay.
Yeah.
Again, so there's time. I think we have time for maybe one or two more questions. I'm just double checking to see if I've missed any raised hands here. Um, let's see. So maybe another question here that I have that I think is interesting on this. I mean, one of the things that you have to kind of consider in these political economy settings is just sort of the anticipation of the actions of other individuals. And so there's sort of two things with that is one, I mean, it's how much is that incorporated into what's going on where you're thinking about I'm in one sector and I'm anticipating the other sector. And
Mhm.
I guess sort of a second question you could ask, I guess, is that, if I think if I understood correctly, you sort of cut things off at like zero emissions, right? Where there is some sort of discussion in the IPCC reports about needing negative emissions in certain scenarios and potentially pushing that. So I guess that's sort of a two-part question. There's one, how much anticipation is going on here between sectors? And two, suppose one of the actions could be introducing this sort of negative emissions, and right, based on the
Mhm.
intensity and the cost, that would mean sort of you might expect one sector to behave one way or another. Uh,
Right.
Sort of your thoughts on those two pieces.
Yeah, for sure, for sure. So on the foresight question, in our case, we are considering we don't necessarily have any like barriers to information or like anticipation of some other policy shock in the future. I think it's important though. Like I can imagine a case where, some sector is, anticipating there's some other policy that get implemented over here. Maybe there's a spillover that they're also anticipating or something like that. And that might change their behavior. On the carbon capture point, I think that's also an interesting wrinkle we could think about for two reasons. One is the first thing I'll say is within our cost calibration, there is some carbon capture that's incorporated within each sector's MAC. So there's within the IPCC, there is like some amount of allocation in individual sectors for carbon capture and utility, carbon capture and storage. So that's partially baked in. The one thing that isn't baked in is like this backstop technology, right? Where you have like large scale carbon removal plants. And on the one hand, I can see how you would implement that by, let's say you just have another sector, right? You just say there's another sector in this model that's really expensive, but it's, the DAC sector. And in fact, I think we did that in the uncertainty paper that I mentioned earlier. Because of course, if you have risk, then that DAC technology can also help you as a hedge as well. The other thing though is I think it's important when you think about overshoot scenarios as well. And I think that if I was, if I was going to study an overshoot scenario or something like that, I would try to incorporate the damages aspect of the problem as well at the same time, right? Because you can imagine like the savings you get on cost are like justified or not justified by how okay you are with an overshoot, right? Like TCRE, to my understanding from a geophysical perspective, is only accurate when you're ramping up CO2 emissions, but when you draw down CO2 emissions, TCRE isn't as good of an approximation of the climate system. So you have to think about a little more carefully about your climate dynamics. And then when you're doing those drawdown scenarios, the carbon budget isn't the right way to think about the problem anymore, right? You have to think about the actual temperature pathway, not like just a budget scenario, right? So if you're going to think about those overshoot scenarios, which I think my impression is that DAC is really important for those in particular, especially if you're trying to reach something like 1.7, 1.8. If you're going like 1.5, right, then like obviously you need to just like implement DAC, like your life depends on it. But if you're doing like 1.7, 1.8, then you have a little more leeway to overshoot and come back. And in those cases, we'd have to think a little more carefully within our modeling framework about like how are we representing the climate as well. Whereas I think the economic side might be a little easier because you'd have another sector that's DAC, right? And have
Yeah.
some learning by doing or something like that. Subsidies in that sector could be an interesting thing to think about in the future, right? Trying to get that to be mature by 2050 when you really need it, stuff like that.
Perfect. Yeah, that's really interesting. I think the overshoot problem in particular is something where you're thinking about those dynamics and how costly damages could be. I think there's a lot of discussion about that. So that's yeah, that's super interesting.
Yeah.
I think we're about out of time unless there's any questions that I've missed. Like Adam has here posted his email as well, so feel free to shoot him an email.
Mhm.
Sounds like not only an interesting project, but a lot of interesting follow-up work as well.
Absolutely.
So looking forward to hearing about that. So thank you so much, Adam. Appreciate it. Just a reminder to everyone here as well. So our next webinar is going to take place February 10th. That'll be Keith Chan and Wilson Wan, both from the University of Hong Kong Science and Technology, are presenting the double-edged sword of firms' commitment to net zero on the carbon risk premium. This was awarded actually one of the honorable mentions for our e-access research prize. So the link for registering to join is in the chat. And again, a lot of great webinars coming up and really appreciated your time, Adam, and your discussion. Looking forward to hearing from more of you in the future and glad you could join us. So thank you so much, everyone.
Absolutely. Thanks for having me, guys.